The march of time. Since civilization's beginning, the great monuments of the ages have been built on the knowledge of the men of science.
One of the most difficult tasks that I had as associate director was the responsibility for dividing up the discretionary funding, essentially deciding which projects to support and which not. Trying to tell Bill McLean that that idea wasn't worth funding. It wasn't a very pleasant task. He always had very good reasons for supporting the projects that he wanted to.
And now, exploration and discretion. Research. The search for knowledge, both abstract and applicable. Systematic investigation. The R in RDT&E. Although sometimes overlooked in the blaze of press that often greets a new weapon system as it hits the battlefield, the payoffs of the station's 6+ decade investment in technology investigation and application have been profound. The products of the station's research and technology efforts are as diverse as the original forward-looking infrared, or FLIR system, and the strange array of catalyst generators for weather modification. State-of-the-art technology for the creation and characterization of high-energy laser components and ultra-precision surfaces. New energetic materials with broad military and civilian application. And chemiluminescent compounds in visible and invisible spectra. China Lakers pioneered novel, reliable syntheses of everything from high-sensitivity semiconductors to high-temperature superconductors. From new conductive polymers to advanced antenna designs. Highly specialized energetic materials and highly efficient propulsion systems. Station advances in mathematics and computational sciences range from numerical theory to advanced image processing and automatic target recognition, and even to early library databases. Research, basic and applied, formed the foundation of the station's full-spectrum capability to support the fleet. It might seem obvious, as the R in RDT&E, but NOTS was the only Navy ordnance development activity to have a complete, dedicated research department. Beginning as the science department and led by Caltech veterans, the seeds of new technologies were nurtured and exploited in the physics, mathematics, and chemistry divisions. Applied sciences included groups for aerophysics, metallurgy, and optics. And the famous ballistics division gathered in some of the station's brightest and most colorful characters. It also produced a generation of the station's top leadership. Over the decades, emerging technologies drove the creation of Earth and Planetary Sciences and Aerothermal Chemistry and Computational Sciences divisions. Not that all research was confined to the research department. Specialists in numerous disciplines from across the station investigated and applied new and emerging technologies, like semiconductors, and polymers, and electron microscopy, and vapor phase deposition, and software. The station's academic ancestry and its concept to crate RDT&E philosophy, combined with a variety of educational advancement programs, university cooperative projects, and excellent support facilities, to create an atmosphere that fostered creativity and initiative. More importantly, The pursuit of basic knowledge was supported by China Lake's leadership and the bureaus, who saw the value of the exploration and exploitation of new and emerging technologies. And station leaders took the rather radical step early on of taxing the development programs a small percentage to support discretionary in-house efforts, exploratory and foundational research projects that would not be funded through the usual channels. These E&Fs, and later B&Ps, would help create and demonstrate technologies for some of the lake's most successful systems. And China Lake has consistently applied the state-of-its-art to more than its own programs. The station has been instrumental in the promotion of technology transfer to the public and private sectors, as well as in the formation and support of the Federal Laboratory Consortium for Technology Transfer. China Lake Research has brought new technology to the station's and the nation's weapon systems, from the radome to the exhaust nozzle, with every subsystem, sensor, and software in between. Adhesives and batteries and diamond surfaces grown on command. Deposition methodologies and chemical precursors to advance the semiconductor sciences. New knowledge of exotic airframe structures and pressure vessels and the methods for explosive forming and welding. Things that reflect and direct the laser's awesome light, or absorb invisible wavelengths to pull bright images out of blackness. And more subtle things, such as the mathematics of randomness and the underlying physical properties of materials. Literally something of nearly everything, from submarines to satellites, and the sensors for both, and the materials, the techniques, the software to advance their capabilities up to and beyond the so-called state-of-the-art. At no other activity were there so many possibilities to discover a principle in the lab, evolve it into a basic technology, apply that to an area of potential benefit, and walk that application through the development process, right into an ongoing or even a brand new development program. And from there onto the drawing boards and into the shops, into the test chambers and onto the ranges, through Mantech and QA and logistics, and at last into the fleet, onto the ships, the planes, the combat vehicles, into the hands of those whose trade it is to protect the nation with the tools the laboratory provides. But that's another story.
The only way to really exploit available science and technology is to understand it. And the only way to fully understand it is by doing research.
I'm doing research in an area that absolutely fascinates me, and I won't get out of that area unless management throws me out.
This is the Navy laboratory, isn't it? So I'm doing research to get things the Navy can use.
What really turns me on about my research work is technology transfer. The idea of creating something here in the lab that's going to get widespread use.
You talk to 12 different people doing research here at China Lake, you get a dozen different reasons why they're doing it. But the point is that important, relevant research is being done here and being done successfully. Well, as an example, let me show you what we're doing. We're trying to test the limits of an assumption that's the basis for a billion-dollar semiconductor industry. The assumption is that despite all we know about bonding and the arrangements of atoms and crystals, electrons move as if they were in a smooth, empty box, moving independently of one another. Our research program represents the first successful measurement of the precise momentum space symmetry of electronic transitions by purely experimental means. We're using the phenomenon of electroreflectance to measure the separation between energy states and their symmetry so that we can test band structure calculations. A sample of semiconducting material formed into a smooth mirror is placed in a high vacuum cryostat. The sample is then positioned in the light path from a scanning monochromator. This produces a beam of controllable wavelength from infrared through ultraviolet. We then apply a strong alternating electric field across the sample. The reflected light is detected and analyzed in two parts, one modulated by the electric field, the other constant. These are then ratioed and plotted against the wavelength of the incident light. The experimental setup is sufficiently sensitive to detect a change in reflected light intensity caused by the electric field as small as 1 part per million. Results have verified the one-electron band structure approximation in greater detail than ever before. Our research program is actually three-pronged. Not only are we interested in verifying the band structure assumption, but we're also very much interested in the phenomenon of electroreflectance itself. A device with a controllable reflectance might be very useful. We're also studying unusual materials for solid-state application, materials that may be less expensive and more reliable than those currently in use, materials with the potential to create entirely new solid-state devices.
The area of solid state also includes the field of metallurgy. We're using the electron microscope to study defects in metals. We are particularly interested in what are known as vacancies, missing atoms in the lattice, because these are known to play an important role in many metallurgical phenomena. For example, precipitation, fatigue, high temperature deformation.
One example of our work includes the study of interactions between solute atoms and vacancies in alloy systems. We start our study by preparing high-purity samples of simple binary and tertiary alloys under controlled conditions. The samples are then rolled to a foil and subjected to a quenching treatment which produces lattice defects. We then chemically thin the specimen to less than 1,000th of a millimeter for direct observation of the vacancy clusters using the electron microscope.
We can then monitor the behavior and the size of the clusters during subsequent annealing experiments. The techniques we have developed allow us to make precise measurements and obtain detailed information on the diffusion of vacancies and their interaction with solid atoms. While it's well known that very small amounts of tin, cadmium, and even gold have an unusually large effect on aluminum alloy properties, we're trying to find out why. We are fairly certain that these trace elements strongly interact with the vacancies to modify the precipitation behavior, and we're trying to find the most effective elements for this purpose. When these studies are completed, we should have the potential for designing superior materials. Ultimately, what we're hoping to do with this research is to provide the parameters that can be used to program a computer. Given any set of desired alloy properties, a computer could then tell us the exact ratio of elements and the required physical operations to yield an alloy with just those properties.
On a more immediate level, our studies help us understand the role of vacancies in the failure of metals by stress corrosion cracking. If we can understand what really causes failure, we should be able to prevent it.
We're also in the business of preventing failures. We're conducting a comprehensive research program into the properties of solid propellants. Our goal is to really understand the combustion process, to pull together the multitude of theories on the subject. One aspect of our work is a study of ammonium perchlorate deflagration on the single crystal level. A prevailing theory was that the material went from solid to vapor by sublimation. Our microscopic studies of the surface reaction during combustion revealed the existence of a thin liquid phase. Subsequent analysis indicated that 70% of the energy transfer takes place within this liquid phase. We now have a much better mechanistic insight into the combustion process, which will enable us to tailor the properties with greater confidence.
Metal particles are used in solid propellant formulations primarily to increase the specific impulse of the motor, that is, to give it more punch. We're studying the combustion of metals in greater detail than has ever been done before. Currently, aluminum is the most widely used metal for solid propellants. The metal, however, tends to agglomerate during combustion and becomes coated with oxide, which inhibits complete burning. We were the first to determine the actual mechanism of particle agglomeration, and we're learning to reduce the process by pre-treating the aluminum before including it in the formulation. We're also studying the use of other metals in propellant formulations. Beryllium, for example. This particular metal has some rather arresting properties. It has the highest heat of oxidation of any metal considered for propellant use, but it produces toxic combustion byproducts and explodes if burned in the presence of nitrogen. If we can understand the combustion of beryllium well enough to overcome its hazards, we think it'll be a more successful propellant additive than aluminum. We're determining particle burning times and examining the nature of the combustion as a function of the burning environment. The size of the metal oxides resulting from the combustion is an essential factor in controlling the motor combustion instabilities, which can actually wipe out the whole rocket. Knowing the characteristics of the motor cavity and the propellant, we can not only predict instabilities, but by controlling metal agglomeration and combustion, we hope to prevent them.
Metal powders are also of interest to us in our work in physical optics.
The big problem, of course, is how can you possibly measure the optical constants of something with the scattering characteristics of a metal powder? Well, you really couldn't, at least not with any accuracy, until we developed our attenuated total reflection, or ATR, spectrometer. The ATR works with the test material in optical contact with a transparent prism. The instrument looks at the sample prism interface where a standing wave is formed, rather than measuring the traveling wave as in other optical techniques. The ATR gives us the optical constants with great accuracy. The instrument even has application in biomedicine for analyzing highly inhomogeneous fluids, such as blood.
The ATR is only one of a family of unique instruments that we've developed. With this reflectometer, for example, we can measure reflectance an order of magnitude more accurately than with any commercial instrument. Success of our reflectometers allowed us to begin a research program on the physics of optical surfaces, with emphasis on mirrors. Now, the two major problems with mirrors are scattering and absorption. Only part of the scattering is caused by scratches or other major surface defects. Much of it arises from submicroscopic surface irregularities, almost as small as the spacing between atoms. Just recently, we've discovered that absorption, as well as scattering, may result from some fairly exotic phenomena, such as surface plasma excitation or possibly polariton re-emission. All of these effects can be significantly reduced by making the surface super smooth. To make a low scattering mirror, you've got to start with an ultra smooth substrate. A typical commercial mirror substrate has a roughness with an RMS height of about 25 angstroms. Now, 25 angstroms is extremely smooth, but we found that it's not smooth enough for critical applications. We've been able to polish to better than 7 angstroms RMS using a technique that we developed here. In addition to surface smoothness, we've also learned that surface preparation is extremely important. We use a system of ultrasonic cleaning, vacuum drying, and vacuum baking. We deposit the reflecting film in an ultra-high vacuum system held at 10 to the minus 9th torr during the deposition to control residual gases. We think that the presence of certain gases during the evaporation may affect the optical absorption by increasing the dislocation density at the surface. Although our research is directed primarily toward an overall understanding, an outgrowth of our work has been the production of the highest reflectance metal coating ever made, very nearly the theoretical maximum. By making the mirror surface more perfect, we've substantially lowered both absorption and scattering. Where this really pays off is in the optical cavity of a high-energy infrared laser. Conventional mirrors tend to absorb too much laser energy, thus limiting the laser output. The use of our low absorption mirrors will make it possible to substantially increase the output power. For the short wavelength lasers, the mirror's low scattering property reduces beam divergence, and it also reduces the backscattering that's been known to shatter the lasing rod.
Breaking a rod is one problem we'll never have. You see, our laser doesn't use a rod. This is a liquid dye laser. And what's really exciting about the device is that it's tunable, rapidly tunable over the entire visible spectrum. And there's a flock of important applications for the rapidly tunable laser. In range finding, communications, and weaponry. To really understand the significance of the dye laser, consider this. Just where would radar and communication technologies be today if they were stuck with a single microwave frequency? The dye laser generates a wide band of output frequencies, as opposed to the very narrow band of other lasers. We tune the dye laser by funneling the energy contained in the broad band into a variable narrow band. One tuning technique uses a diffraction grating to generate the narrow band output. By changing the angle of the beam with respect to the grating, we obtain different output frequencies. Since we can't oscillate the heavy grating at a high frequency, we insert a small, rapidly oscillating mirror between the dye cell and the grating. Thus, the angle of the mirror with respect to the grating governs the output frequency. We have another tuning technique that makes use of a scanning interferometer composed of two mirrors that are flat within 2/100th of a wavelength and parallel to better than a second of arc. Constructive interference occurring between the plates creates a narrow bandpass filter. By changing plate separation, the passband is changed. The laser will then only operate at the transmission wavelength of this variable filter. Both tuning techniques are unique, and we have applied for patents. The dye laser has triggered considerable research in the area of organic dye chemistry. Even slight improvements in the purity of dye have significantly improved laser action. Presently, it takes a number of organic dyes to cover the entire visible spectrum, but we've got some pretty sharp chemists working to minimize this number. Right now, we're pumping our experimental laser with another laser.
However, there is a remote possibility that we can pump a dye laser by chemical means. Our group is working on techniques for producing light by chemiluminescence. A number of years ago, we began experimenting with a DuPont material that glowed weakly when exposed to air. So weakly that you can barely see it. DuPont wasn't particularly interested in developing the chemical, but we were fascinated by the oxyluminescent mechanism. Little by little, we began to increase the light output. Pretty soon we realized that we'd milked this system, and we looked elsewhere for something more promising. Based on our success, American Cyanamid had developed a brighter system, and we began cooperating with them to improve the chemistry. The reaction is between an oxalate ester and hydrogen peroxide, which with a proper catalyst results in the excitation of any included fluorescer. The peroxide oxidizes the oxalate to high-energy molecules, which react with the dye, causing it to fluoresce its characteristic color. We began to improve the reaction, and we've managed to just about double the light output each year. We're at the point now where we've got a product. A good one. Now, it's nothing that's going to set the world on fire, but a cold light like our chem light comes in pretty handy for applications like emergency lights or for target marking. Okay, so maybe we won't be able to pump a laser with our chemiluminescent system, but we feel that it's our responsibility as researchers to consider even the remote possibilities for other projects.
As a microbiologist, the help of the chemists here at China Lake enables me to expand the scope of my research. We are working to isolate strains of oil-digesting bacteria that can be used as an effective means of destroying oil slicks in the ocean. Typically, oil is composed of many different hydrocarbons. Some of the more volatile ones evaporate rapidly. Before the oil becomes a thick, gooey residue, we want to have bacteria digest as much as possible. The bacterial cell mass can then serve as a source of food for the resident marine life. So far, we have isolated a number of strains of marine bacteria which appears to be strong hydrocarbon oxidizers. Experiments with the Louisiana crude oil have shown that the bacteria can ingest 50% of the hydrocarbons within a 48-hour period. We feel that bacteria can be a useful tool to fight oil pollution in the ocean. Of course, the proper technology still remains to be developed. It is interesting to see how we can exploit nature to protect nature.
Well, that's our approach too, but on a far more paranoid scale. Our field is weather modification, and there's probably no scientific area so filled with controversy and with charlatanism. Our research group is composed of physicists, engineers, chemists, and mathematicians. We don't predict the weather, we make it. Our job is first to understand weather phenomena and then work to manipulate it. We were there to relieve droughts in the Philippines and to fill reservoirs in Okinawa. We have the hardware, the techniques, the basic understanding, and we're transferring this technology from the laboratory to the real world. For example, the early acetone burners used for cloud seeding were producing erratic results. It had been assumed that the burners were generating pure silver iodide. Instead, we found they are actually producing a complex containing sodium iodide. We've not only improved acetone burners, but we've developed a miniature pyrotechnic device that can generate pure silver iodide in the midst of a cloud. What it all boils down to is this. Weather modification is not subject to the whims and idiosyncrasies of Mother Nature. Weather phenomena are governed by immutable and reproducible laws of physics.
This idea of reproducibility is probably the most important criteria for competent research. This is especially true in our area. We're studying the possibility of using amorphous or disordered materials as semiconductor devices.
You know, one of the big problems in the semiconductor business is the amount of time and money you need to produce the crystalline raw materials and then fabricate the devices. Now, we're not the only ones studying amorphous materials, but since we can draw on the background and experience of the entire center, we're getting results that no one else has. We're depositing high-density, highly reproducible films in a vacuum on the order of 10 to the minus 9 torr. In order to avoid atmospheric contamination of our newly formed amorphous material, we do our testing in the same chamber where the film was formed.
You know, there's been a lot of disagreement about amorphous semiconductors. Let me have those pictures. Take a look at these. See these physical voids in the film? It turns out that their presence or their absence may account for a large part of the disagreement. These voids had been predicted by indirect methods, but we were the first to prove their existence by direct microscopic observation.
We can make amorphous films with voids or without the voids, so we're doing both to try to determine which properties are affected by them.
Because of the techniques we use, we're finding that our amorphous films are excellent photoconductors, an application that's been pretty much overlooked by other investigators.
We've demonstrated rise times faster than 1 microsecond and a practical detectivity. We're now in the process of actually fabricating some devices to see how they function in a work environment.
Amorphous semiconductors are the next logical step beyond crystals. They're cheaper, they're more rugged, and they're not damaged by radiation.
And because of their properties, there's a good possibility we can tailor the band gap to get any kind of response characteristics we want. And from a theoretical standpoint, the materials are fascinating. We've been studying some of the more exotic phenomena, such as hopping, which is a form of transport unique to disordered systems.
You see, the thing about amorphous semiconductors is that while the material is easier to form than crystals, the physics is really a bitch. So we need the basic understanding in depth before we can really exploit the phenomenon.
Probably one of the most exciting phenomena in recent science is superconductivity. At extremely low temperatures, the electrical resistance of certain metals becomes zero. If you start a current flowing in the superconducting ring, it will continue to flow on its own for about as close to forever as you're likely to get. We're experimenting with what is known as the Josephson tunneling effect in hopes of developing a low-noise detector of electromagnetic wave radiation. Now, the classical Josephson junction is composed of a thin sandwich of dielectric between two slices of superconducting material, almost like a capacitor. When the junction is cooled below its critical temperature, exposure to electromagnetic radiation causes a change in the normal Josephson current flowing through the junction. This type of Joe junction isn't practical as a military device because it's mechanically unstable and deteriorates with age. We're doing research on a device called a weak link, which has all the properties of a Joe junction, but none of its disadvantages. A weak link is a single piece of superconducting material with a very thin neck. Weak links aren't available commercially, so we have to fabricate them in-house. It's a bit of a hassle because the neck is only about 1 micron. It has to be that thin or the device just won't work. We're using a scribe film technique to obtain necks even smaller than a micron. We're working with niobium nitride because it has a relatively high critical temperature, around 17 degrees Kelvin, so it doesn't need liquid helium to start its superconducting. We put our devices in a cryostat, expose them to radiation, and analyze the output. So far, it looks like we're in the ballpark. Oh, we have our problems. The device may be simple physically, but that math sure gets hairy.
Mathematics plays a dual role in research. We're using math as a tool to solve other people's technical problems.
And we're doing basic research in the field of mathematics. One activity reinforces the other. For example, my specialty is abstract algebra, which deals with mathematical systems such as groups, fields, and linear spaces. You see, abstract algebra is sort of like a fine set of tools. You've got to keep working on them so they'll be ready when you need them. Now, when a difficult problem in radar signal coding came along, I was able to use these tools to analyze the problem and devise a successful solution. Okay, a solution could have been obtained without the use of algebra, but at the cost of how much more computer time?
Now, in the area of engineering support, we're doing a great deal of work on the optimal control and guidance of missiles. Given a complete set of parameters, such as weight, dimension, shape, and thrust, we first construct a mathematical model and then use the computer to calculate the details for trajectory and control optimization. Sometimes our mathematical results defy intuition. For one set of parameters for a specific air-to-air missile, we discovered that if the target were to perform certain basic evasive maneuvers, that the missile would just never impact. This type of information is invaluable for the development project.
Now, we don't claim that we make the system work. What we do feel is that we save considerable time and effort and pain in getting it to work.
That's how it goes with mathematics.
And that's how it goes with research. I guess what it's all about is this. If your business is national security, You've got to have a good staff of people doing research. It's no gamble. You're loading the dice in your favor. You're bound to benefit in many ways, surprising, unpredictable ways. Well, what more can I say?
Occasionally, the need arises to look at something that is difficult to see by ordinary means. A scanning electron microscope has been acquired by the Naval Weapons Center to aid in research. Of prime importance is the ability of the microscope to look at specimens directly. There is no need for the sectioning or flattening that is often necessary when using conventional types of microscopes. Operation of the scanning electron microscope requires the specimen chamber to be evacuated. Pump down to working vacuum is accomplished rapidly. Images are formed by electronic reconstruction rather than being transferred through lenses. All viewing is done from electronic displays. The scope on the right is a special purpose cathode ray tube used to obtain a photograph of the specimen. The use of Polaroid film yields a rapid, detailed, and permanent record of specimens under examination. Picture quality is excellent, permitting sharp photographic enlargements. The scanning electron microscope is proving useful in a variety of fields. One example is the microscopic study of ammonium perchlorate crystals, which is helping to understand the role of oxidizers in the formulation of solid propellants. The most outstanding features of the microscope are its extreme magnification, up to 25,000 times, and its enormous depth of viewing field. Even at highest magnification, sharp focus extends deep into the specimen. Another example of the microscope's use is to evaluate lead sulfide films deposited during fabrication of photoconductors. Crystals of ice are almost invisible to the naked eye. Investigation of their structure contributes significantly to the center's nucleation and seeding studies. Magnification here is in excess of 10,000 times. The scanning electron microscope has proved invaluable for solving sophisticated scientific problems.
The effect of the pinna on a person's ability to localize the source of a sound is one of the very interesting exploratory research projects undertaken by the Naval Ordnance Test Station. The project began about 3 years ago with a demonstration of the effect of the pinna to Dr. Bateau of United Research Corporation by an experiment involving the jingling of keys. We'll try to reproduce this experiment for you again. If Dr. Bateau will close his eyes, I'll try to test his ability to locate the source of the sound. Now, if you distort your ear lobes, or the pinna, you find that the whole character of the room has changed and your ability to localize the source of the sound is much decreased. You want to close your eyes again? This simple experiment has led to a number of theories and results which Dr. Bateau will explain to us in more detail.
After we'd made these observations of the effect of the pinna on localization, we needed to develop a hypothesis. We needed some logic to tell us what to do next, and we needed some knowledge of literature so we'd know what other people had done. The first logical step is that obviously you need a coordinate system to say where a point in space might be. This coordinate system must have an origin and 3 points which tell you what the coordinate lines are. From the literature, we found that a great deal of concentration had been placed on the fact that you have 2 ears. If we think of these as just 2 holes in the head with a line connecting them, it certainly isn't sufficient to give us the space coordinates we need. The general idea was that a sound out here would arrive at this point later than it would arrive here. The difficulty is that there is a surface like that, any point of which provides the same time difference between the 2 ears, so that you couldn't know whether it was inside your head or outside or anywhere on that surface, so that the time difference is an inadequate explanation for the localization of sound. Some researchers added to this the idea that you have a head between your 2 ears and that the sound arriving from here will be weaker than the sound arriving to the ear on the same side as the origin of the sound. The same argument applies to this condition as applies to this. If we use amplitude differences, we will again generate a surface of ambiguity, and everywhere on that surface the amplitude ratios between the 2 ears will be the same. Even if we combine these two, we will not have a sufficient space. We will have a line of ambiguity which is given by the intersection between the 2 surfaces. Some other researchers suggested that you develop a coordinate system by first having your ears in this position, and let's say in this position, and then in this position. This will certainly provide a coordinate system which meets our requirements, but it has been observed that you can localize the sound without moving your head, and the motions required are fairly large and not minute motions that might have been thought to be sufficient by some researchers. We still need a transformation of the sound onto the hearer which will permit him to develop a coordinate system which will tell him where it's coming from. We found one paper by Angel and Fite. I mention it because it was the only one that we found and that it was important on monaural localization It was published in the Psych Review for 1901. And we found a few mentions of monaural localization by other people who had not done much work in it. This essentially said that you can localize with one hole in your head. We know that logically that's impossible. But if we take our observation about the pinna and add the pinna to the hole in the head, we have the possibility of having a mechanical transformation which will permit us to localize and is similar to the time development of a coordinate system, but is done in a static system of delays. I can summarize what I've just said by stating the requirements we thought were necessary logically and how the necessary requirements might be met by hypothesis. Requirements: the transformation of the incoming waves is needed for localization. The transformation must be different for each different aspect of the source relative to the hearer. The hypothesis: the external ear can and does perform the required transformation. The next step in our research was to test our hypothesis. In order to test our hypothesis, we found it necessary to construct a duplicate of the mechanical structure of human hearing. First thing we did was to cast the ears of one of our engineers in silicone plastic. From this casting, we made a replica of the pinna. We took the pinna and put it in place on an ordinary closed dummy. Inside the pinna, inside the head, are microphones of as high fidelity as we could get. Around the microphones are lead isolators to keep the sound from arriving to them from anywhere except through the ear canal. The head is then filled with sand and wax so it won't sound hollow. When we had completed the construction of the head, we produced a sound of the click with a small loudspeaker and observed the resultant waveform on an oscilloscope. When we did this, we saw a small feature that moved smoothly from the beginning of the trace when we were at the back of the head to the middle of the trace when we were at the side and to the forward portion of the trace when we were in front, as if the signal had been delayed by differing amounts as you went from back to front. It would be useful for us first to look at sketches of the waveforms associated with localization, and then to look at the actual oscilloscope pictures. From the rear, the oscilloscope trace looks very much like it does to a bare microphone. As you move towards the side, a feature develops and runs up the slope of the waveform and produces a notch at the top of the waveform. As you go to the front, this notch runs down the other side of the waveform and produces a shoulder. This looks very much as if this feature had been delayed and added to the waveform with varying delays, the least delay here, more delay here, and still more delay here. The delay from the rear appears to be about 2 or 3 microseconds. The delay from the front appears to be about 160 microseconds. We'll use the oscilloscope to present the waveforms of localization. I'll use this small speaker to generate a click, first from the rear of the head, then I'll move slowly to the side, and then to the front. You can watch the feature move on the waveform as the sound source moves about the head. Then I will move the speaker slowly from front to back. First, the sound from the rear of the head, with the feature showing at the beginning of the waveform. As we move towards the side of the head, the feature slides up the slope and forms a depression at the top. As we go on around towards the front, slides down the other side and forms the shoulder. From the front, from the side, from directly and back. At the back, towards the side, at the side, towards the front, at the front. Now towards the side. From the side, now going towards the rear. Now at the rear. The final test of our hypothesis is for a human being to localize through an electronic system which has ears with the microphones, such as we have constructed here. Those of you who have headphones, put them on, and you may hear for yourself. Demonstration was interesting, or would you have preferred to hear it from this side? I hope that those of you who didn't have headphones for this demonstration will have an opportunity to hear one of our demonstration tapes. From the work we've done in human localization and the observations we've made, there are two conclusions that can be drawn. One, the external ears perform an important function in human localization. And two, that function is performed by the pinna introducing time delays in the path of the incoming sound to the eardrum.